Okay. So this is always a challenging time, you know, there's after lunch and people are beginning to go to sleep. So try to hang in there. So I'm going to talk a little bit at a high level about, well, first I should show you what the name of my slide. This talk is a complete high integrity software development stack. So presumably we know what high integrity is. Some of the terms there you may not be using every day, but our customer base is largely people like you who are trying to build systems that you hope will not fail, and in some cases, if they do fail, people die. We take that very seriously, and all of our tools are oriented around helping our customers build high-integrity software. We are certainly seeing a move towards model-based development, and this is going to be talking a little bit about that process and how we're reacting to it. So things have maybe gotten a little better than this, but I will say not long ago I heard almost exactly these same things from people out there. Systems engineers say, who needs programmers? Why do we have to depend on them to implement our design? And I do think there's a general sense that the system engineers understand the system and the software engineers don't. And so why, you know, isn't there some way we can kind of cut them out of the process? On the other hand, the programmers are saying, oh boy, not another attempt at programming with pictures, you know, oh, that'll be great, you know, you just drag and drop and everything's going to be wonderful. You know, I think hopefully both sides of this little battle are getting a little more mature about what's going on, but maybe not deep down where they, you know, keep their secrets. So who's really in charge? You know, is it, do we really need programmers? That's an interesting question. I think the system architects and the system engineers, they develop the original design. To some degree, they have the big picture. And unfortunately, in a traditional environment, there's kind of a handoff. And having made that handoff, you sort of see this gorgeous design with this great high-level idea begin to evolve. And, you know, the software engineers don't necessarily fully understand what's going on. And they say, well, it'd be more efficient to do it this way. And we'll cut out this little piece of functionality or add something here because it'll look better. And after a while, your wonderful design and even your architecture might evolve as the software development proceeds. And then if something goes wrong, of course, there's an us versus them. Well, if you'd stuck to the original design, this wouldn't have happened. So, well, if that original design was broken, there was no way it was going to work. We had to make fixes during software development. So, you know, it's a little bit of a frustrating situation where you don't have that direct connection, and the design, the high-level design, and the detailed design begin to drift apart. So what's the wonderful solution to all this? A friend of mine, Ed Seidowitz, some of you may know him. He's been very involved with model-based development. In particular, he's been very involved with creating a true executable semantics for UML, which is a bit of a challenge because UML tends to have got the reputation of not having much in the way of any semantics at all. So actually getting to execute would be a challenge. He helped design this language called ALF, which is an action language for the foundational subset of UML. Anyway, you probably would all recognize these kind of ideas. He's very focused on standard-based this and standard-based that, so that word standard appears a few times, which is a good thing from a commonality point of view. But even before you get to all of these standards, model-based development is an interesting thing to consider. So how does model-based development help this thing? And I think the main thing is it doesn't necessarily require a handoff. That is, you can actually have a cooperation going on here where the high-level system design is directly turning into something that can, in fact, be executed. So have we really cut the programmers out of here? Well, I hope not. That's sort of what I'm spending my career doing. But I think, in fact, it's a little bit naive to say, well, we've pulled the programmers out of the problem because I write my model and push a button and out comes an executable system. Well, first of all, somebody wrote that program whose button you pushed. That was probably a programmer, a software engineer. The other thing is that those building blocks out of which your beautiful model is constructed are typically relatively low-level things that are built and designed by programmers. And the need for them, what are the ideal building blocks for an aerospace, a space system, or avionics, or automotive, and so on, that's going to vary. And that's obviously going to be, again, derived from the requirements that exist in your particular domain. But this split between the overall high-level view being provided by the system engineers, system architects, and these parameterized building blocks being created and honed and certified by software engineers, I think is actually a very useful split. And I sort of see that the direction that the world is headed. And that's really what software engineers should be creating, are these parameterized building blocks. And I've given them even more little permutations: parameterized, annotated, high-performance building blocks, and from our perspective, high-integrity building blocks. That is, these are things that you can actually put a lot of energy into because they're going to be reused. In a lot of ways, that is, in my view, the key to reuse, is to having these parameterized building blocks that have been used on past missions and so on, and are part of a overall stack, if you will, where they can be easily plugged in through modeling tools and so on. Why is Adacore interested in this? We're a compiler company, I thought. Well, a little bit of a wake-up call. Model-based development, one of our major aerospace companies, essentially they shifted all of their engineers over to modeling. Oopsie, what did I do? Wrong direction. Boop, boop. There we go. And after that, the remaining number of seats that we sold to this company was 5. And before that, it was a much bigger number than 5, orders of magnitude larger. And who were those people? They were their tools group. Well, that's nice to know that their tools group is still using our product, but what about all the rest of the engineers? Our traditional engineers were disappearing into the ocean there of model-based development, and we clearly needed to broaden our focus. And I think it's kind of an exciting thing to do for us because, it's getting us out of our comfort zone a little bit. But I also think it's creating a unique opportunity to have essentially one company able to bring you across this entire stack. So I think everyone's used to the notion of a stack of runtime, where you've got the lower level, BSP and the operating system and so on. Here I'm talking about the software development stack. And it's a little bit like the famous V, where you've got, the design comes down here, you code up here, and so on. But it always seemed unfair to put the coding at the bottom of the V. Like, we're the low-level grunts who, kind of shovel the stuff across, and then all the high-level stuff happens up there. So I'm trying to be a little bit more, you all depend on us is really what's going on. So architecture, modeling, at that level, you might still be doing both software and hardware. And then I've shoved the hardware into the little tiny corner on the right, when all the interesting stuff now these days is in software, of course. And then you've got the coding and the verification. We have been emphasizing verification more and more in our business, and I'll mention the tools that we now have. But that was already becoming a big part of our business, and modeling is now going to increase the level of the stack that we can support. So I thought I'd give you a quick history of Adacore. Some of you know who we are. But this was what the world looked like to us. We had a really nice hammer called GNAT, which is an open source Ada compiler. And if you had a nail that looked even vaguely like a nail, we would let you hammer it with this one product. And that's what we call classically a one-product company. And I think we did okay. 10 years later, the company begins to look like this. We still got that hammer. We're really happy with that hammer. We gave it a little bit longer name. It's now called GNAT Pro. And we can handle more targets. And we've got like this really nice box in which it all fits in, which we call the GNAT Programming Studio. But that's still, it's pretty much that one hammer is what we're really selling. We've kind of wrapped it around a lot of other things, but that's a really good hammer. So in the past 10 years, we now have a bunch of more precision tools, I will say, and it looks a lot like a dentist chair, so I'm a little bit scared of it. But CodePeer is our static analysis tool, which also is similar to Polyspace and some of the others, where it's a formally based tool. And so when it says this will happen or won't happen, that's based on some real formal analysis. We also have a GNAT coverage tool, which is very important for some kinds of people like you where testing matters. And that's actually based on the QEMU technology, which allows us to do coverage without actually having to alter the code at all. It's essentially a simulator. It also can take input for its tracing purposes, not only from QEMU emulator, but it also can take it from the Valgrind system, which essentially instruments binary code, and the hardware probe of some sort. So GNAT coverage is becoming a bigger part of our business. And then Spark 14, which is the formal subset of Ada that's designed to allow you to do formal proofs of the correctness of your program. And I'll mention a little bit more about that in a second. So here is the overall product line as it sort of exists today. We have that nice hammer at the top there, Gnat Pro. And it's not just Ada anymore, folks. You can also get C and C++. We're essentially one of the largest companies that supports GCC technology from bottom to top. So pretty much if you're using GCC of any sort, be it Ada or C or whatever, GDB, that sort of thing, we have probably more engineers than almost anyone focused on that technology. We have lots of different runtimes. We have a lot of emphasis on VxWorks, but also on Lynx OS and various other operating systems. We also have bareboard systems where you don't need an operating system at all. You just use essentially a glorified Ada runtime that also acts as an operating system. And then there's zero footprint, where you actually don't want an operating system. You really want you want to have bare minimum, very, very little code where you're trying to create, let's say, a secure kernel, and every line, out-of-line bit of code is bad news because you have to certify every line of code. I mentioned this Gnat Programming Studio, which is our own. It's based on the GTK graphical user interface system, and it includes a visual debugger based on GDB. And we also have an Eclipse-based IDE called Gnat Bench, which was originally based on the VxWorks, so-called Workbench, but now it's relatively independent. Gnat Coverage, I mentioned that. It can also use Valgrind. CodePeer, I mentioned that. And it uses control and data flow. It essentially takes the optimizer pass of a compiler and says, I don't care about the quality of the code. What I want to know, I don't care about the quality of the output. I want to know how good is my source code. And so it's based on compiler technology. One of the cool things about it is it actually will generate for you human-readable pre- and post conditions based on what you wrote. So essentially it creates as-built documentation in the form of pre- and post conditions and various other interesting things like test vectors and so on that it gleans, it infers directly out of your source code. So if you want to be moving towards a more formal approach using pre- and post conditions and so on in your code, you can use CodePeer as a way to instruct your existing programmers and to take your existing code and move it towards a more formal view. And then finally, we have the tool set based on this Spark subset of Ada, which is really focused on formal verification. If you've got to do a secure kernel, or you've got something at DO 178 level A, or something like that, then it's a very formal thing. It's now been totally rebuilt over the past 4 years. It now incorporates Ada 2012's new pre- and post-condition syntax, so you can write your own pre- and post-conditions in a way that they can actually be executed by the compiled code and be formally verified by your tool suite. And it's also, the back end is now, instead of being kind of a homegrown Prolog-based proof tool, it's now using SMT solvers, and it's set up so that, in fact, you can plug in different SMT solvers. We bring along, when you get this product, two open source ones, CVC4 and Alt-Ergo, and you can also use it with things like Z3 and so on. There are a number of SMT solvers out now that are, there's been enormous improvement in the quality of SMT solvers over the past decade. There's this sort of annual competition, and they keep leapfrogging each other. Z3, I think, is recognized as one from Microsoft Research, one of the best. But anyway, so that's when you get to the point where you really want to prove every line of code. So that's where we are now. Where are we heading? This is the new, beautiful picture here of what's the future look like. We're putting a lot of energy into a new product we call QGen, and I think I wasn't actually aware of how much use of Simulink there is in this, or at least at this meeting. There seems to be a lot of use of Simulink. Whether it is a representative of all space development, I don't know. But this is a tool that is an automated code generator for Simulink, and it's specifically oriented towards high integrity development, as opposed to just sort of, let's get an executable program out of this model, and how you go about doing that is not necessarily that much interesting. We focused on the actual transformation that's taking place from the Simulink model to the generated code, which can be MISRA C or the Spark subset of Ada. And we are going through the process of qualifying that code generator in the sense of proving that it actually does what it claims it's doing, so that you can have confidence that the code generated from the model is equivalent semantically to the input. It also is designed to be very easy to read and easy to trace back to the model. We heard some discussion earlier of what's involved in doing some of that traceability, and that was one of the goals, again, because we know that for high integrity systems, traceability is essential. So we've been actually focusing initially on the automotive market, because Simulink is a big player in that market, but also we're seeing interest in aerospace as well, and we think this is going to be a very important product for us. We use CodePeer, which is our static analysis tool, as a code verifier, so that it comes sort of as part of the product. It will automatically verify the code that comes out of it, that it satisfies various interesting rules, no runtime errors, and so on. And it's in beta test, so if you're interested, we'd be interested in hearing from you. This is sort of taking it all and trying to say, what do we mean by this high integrity stack? And the idea is that coming at the top, you've got your executable specifications, your system models, and some perhaps verifiable system invariants. And those are feeding down through this set of tools, ultimately with the thing coming out as some kind of certified software-intensive high-integrity system. And we'd like to kind of be your partner all the way along that stream. At the top, you're trying to do simulation. You're trying to verify the system properties. And then we have this QGen product, which is doing a qualified transformation into Spark or into Spark or into C. And coming in from the side there, this is the part that where the programmers still play an important role, are these certifiable libraries. This is not just all new code. There's going to be some significant amount of functionality that is coming in from libraries, from these building blocks, and so on. And it's very important that that code also be certifiable if you're building an overall high-integrity system. And then all of that can be run through Gannett coverage and through various other certification tools. And finally, the goal is to get that overall certified system. So that's where we're headed. And our ongoing vision, got to get that big statement going, provide a broad spectrum of open source. We are an open source company, as is OAR. Open source language technology and high integrity building blocks to help our customers engineer their increasingly complex software-intensive systems. Doesn't that sound like a great vision? One that I can get behind, anyway. And if you have questions, Steve Baird is up there, and I'm right here. And we'll be here until tomorrow. And we'd love to hear from you if you have any questions about where we're going. And our website is, not surprisingly, what it says there. Anyway, I'm available for questions. Thank you. I'm always seeing the same hands here. Can we get some?
Well, should I?
No, I'm just kidding.
Can you go back to a slide where you had layers of tools? You had an architecture, you had a model-based, and you had a... Right there. So what is the difference between architecture and modeling tool? I mean, don't you model to build the architecture?
Well, if you're familiar with AADL, it's an architecture, I don't forget what the other say, design language, yeah, architecture, analysis, and design language, something like that. Anyway, you could do it all with a modeling language, but when the system gets complex enough, trying to have one model, which represents the entire system, gets out of hand. So at an architecture level, you can have one architecture, and then there are places where the different subsystems, which each have their own model, fit into it.
So the top layer, that architecture is the system architecture.
System architecture, okay. Exactly. And you can do some useful stuff at that level as well, obviously, in terms of overall latencies in the system and that sort of thing. But like ground system would be one component of the overall architecture, whereas typically there'd be two separate models, or many models. Other questions? Yes?
Thank you. Does it support C++ programming languages?
Yeah, I mean, we support Gannett. We support GCC, C and C++. Our QGen tool generates C or Ada, and our coverage tools support both C and Ada. So essentially, the C, C++, Ada are our focus.
Thank you.
When you prepared the new concept of the software development stack in response to the change in the customer direction, and that seems like it was somewhat of an existential crisis at that point. Is there also
For some of us, yes.
Yeah. Is there also a change in direction for the Ada language itself to include more direction to these statements? Like, has there been an update in the structure? Not like necessarily like a C to a C++, but has there been additional thought put into new constructs, new backend, new compiling steps to try to implement this approach?
Well, Ada 2012, which is the latest rev, there was a lot of focus on contract-based programming, pre- and post conditions, type invariants, subtype predicates, that sort of thing. And that isn't directly related to this shift, but we do see that thinking at a higher level, thinking about invariants, that sort of thing is the kind of thing that modeling people do. And so, there is that aspect. No, I think there are people who still, have not bought into this model. I think not at Ada Core. I think at Ada Core we're definitely, but we've also got customers who don't believe in programming with pictures. They believe in, hardcore coding. So we're trying to support them as well. And the other thing is that some people do modeling, or at least, some degree of specification by just using Ada packages, Ada package specs. That becomes kind of their model. And at that level, they really want to be able to specify the pre- and post conditions, for example, and the invariants and so on. So in some ways, some people are trying to stick with programming languages and move up to a higher level. And when they do that, they definitely want to talk about things like invariants and so on. So, there are different ways of trying to skin the same cat. I'm a big believer in moving towards modeling. I'm not convinced that Simulink is the final answer in terms of modeling languages. And so all of our technology is designed to handle multiple or different kinds of modeling languages. Not that much of it is Simulink specific. It's more of the general principle of transforming something that's represented as a model, either state machine or a synchronous data flow kind of thing, into a more conventional programming language.
Okay, I guess.
I don't do much with Simulink, but a lot of people, or a lot of the GNC guys at our company do their control algorithms with Simulink. So I guess, you kept saying you're targeting, high integrity development. I'm wondering if you could just talk to why somebody would use this tool versus the Simulink autocoder. What are the advantages of and again, I don't use it, but maybe I'm missing something.
In our experience with our initial round of customers, and also prior to actually beginning development, this grew out of a project that was done in the European Union and called Project P. Not I don't know why they called it Project P. They couldn't think of another name, but it basically people are frustrated with some of these autocoders because they aren't qualified. They don't give any real guarantees about, obviously they're not trying to insert bugs. That would be a little bit weird. But they're not going out of their way to qualify these tools so that you can then take them to somebody like the FAA and say, I don't need to retest everything I tested at the model level because I used a qualified tool to produce the code. So in terms of the testing effort, one of the goals of all this is to reduce the dollars per line of code to get the same level of quality. So, the estimates I've heard is, typical software, $10 per line of code. Aerospace software, $100 per line of code. High security software, $1,000 per line of code, or something like that. And as was mentioned earlier, half or more of that is all about qualification, certification, that sort of thing, testing, et cetera. And if you have to retest the output of these tools, that's a real drag. You've got to go through all of the same process again, even though you didn't even create the code. So it's very hard to, if you find a bug in it, you're like, oh God, I've got to trace it back to the model and so on. So we're trying to reduce the cost of model-based development and satisfy people like the FAA that you don't have to do all this retesting. They also claim that the output of our tool is a lot easier to read and understand, and that seems like something that could also be very relevant when you're trying to do some real significant testing. Yeah. Okay. Thank you.